in the series of basics of software defined radios and practical applications, we were discussing power amplifiers, how to select the power amplifiers, and today we will discuss the power amplifier lineup for linearity and power requirement calculations. So, yesterday we have studied this problem statement. We had to design a PA system, PA assembly, so that we can achieve at least 10 watt average and 80 dB gain at the output of this assembly, and the PAPR of the signal, which was the LT signal, was 10 dB, and we had to meet the linearity criteria of C by IMD3 of 45 dBc, and we should be able to avoid the clipping. Now, after that we were supposed to specify the output power back off operating point, gain, as well as linearity of the finely designed amplifier assembly. Yesterday we had done this exercise by using the power amplifier with the particularly given specification, and these were the specification. Now, today we will discuss how we can select among different power amplifiers. So, in the previous lecture we did not have any choice, we were just given one amplifier and we had to design based on that. Now, today we have number of devices among which we can select. I have taken this sheet again from the mini circuits, and as you can see, we can see the model number, then we can see the frequency range, gain, P1 dB, maximum input power without damaging it, IP3 value, and because we are given the P1 dB, from IP3 value we can actually see that which one is the most linear among these. Apart from that, we are also given the voltage and current values, and based on those values we can have some idea about the DC power consumption. Now, in this sheet you can also see that they are showing connectors N, SMA and N. So, let us quickly go through the different types of connectors. These are different type of connectors. SMA type connectors, this kind of connectors, and they are known as male or plug, and female or jack type of connector. Another type of connector which can support high power are N type connectors. This is the picture of an N type connector, and these are BNC type connectors. This kind of connectors, they have a slot where you can actually put the pin and then you can turn it around and it will be locked into this small slot. So, these BNC type connectors can be used to actually divide signal into different parts or combine signal. So, for example, into this kind of BNC type connector, you can add 3 of these connectors and it will break the signal which is coming from this path into these 3 paths. Now, these kind of connectors can be soldered at any equipment end, or they can be soldered at the end of a particular cable, and based on whatever is required you can select these connectors. So, if we go back and look at this, we can see here that initial 4 are using N type connectors. So, in that case you should have cable with a N type connector handy, so that you can actually attach those power amplifiers with your system. Similarly, 3 of the devices they are using SMA kind of connectors, which are this kind of connectors. So, your cable end should be like this to receive or to send data to this kind of devices. So, these are different kind of devices and their values are given. Now, we will again go through our original problem, and which was designing a power amplifier. So, let us note down our key ideas. So, first of all, P out from system. So, yesterday we have calculated that 10 watt should be equal to 40 dBm, and because we are using a signal with 10 dB PAPR, so we should be able to provide this signal without clipping it. So, if this is the average power, then to allow for the peak of 10 dB, the actual P out without clipping would be 50 dBm. So, this is the output power requirement. So, first requirement is this. Second, linearity requirement. At the output, assembly should have C by IMD3 ratio of at least 45 dBc. And how this criteria was effective there, because this was the C by I ratio we have to maintain. So, we have to work at a particular power backoff for our for our solid state power amplifier. So, what was the formula? 20 plus 2 times OPBO was equal to the C by IMD3 ratio. Now, this is a particular formula which is applicable to all SPA. It gives us some idea how we can take our output backoff. According to this, our OPBO was coming out to be 12.5 dB. So, whatever is the output power we can get from any device, our device has to work 12.5 dB lesser power than what we can get from the device actually. So, this was the linearity requirement, and third requirement was gain. So, we should be able to get 80 dB gain from the system. Now, if you look here, today we have added one statement, operating frequency is 2 gigahertz. So, let us start choosing our components based on that. First of all, our operating frequency is 2 gigahertz. So, it should, our frequency range should be able to cover that frequency. Based on that, among all these devices, we have selected these 3 devices, because other devices are from 2.5 gigahertz to 6 gigahertz, which is beyond this. Again, these 3 can be the part of this one, from 6 to 18 is away, 6 to 18 is away, and again this is lower than what we require. So, this and this, actually 4 devices are there which are fulfilling the criteria which we require. So, keeping this in mind, now these are the 4 devices we can play with. So, now let us start our calculation. And how do we start? First of all, we have to maintain this output power backoff, but at the same time we need total output power to be 50 dBm so that we can avoid clipping. So, because we want this power which is a very high power, so we have to choose a device which has a very high P1 dB. So, if we look here, this device HPA 272 plus, it is having highest P1 dB with respect to the other available components. So, let us choose HPA 272 plus for the last stage. So, design of the last stage, HPA 272 plus has been chosen. Now, P1 dB point here in this case is 49 dBm. So, device can provide output power at 1 dB saturation. This is the definition of P1 dB point. But because we have to drive our signal at 12.5 dB back off, so that we can avoid the clipping, device can provide 49 minus 12.5, which is 36.5 dBm output power for C by I3 ratio of 45 dBc, which is required. So, this is the power we can get from one device. In the last lecture we also discussed that when we have some of these devices, how we can do the calculation of number of parallel stages, and we have discussed that when we add two devices together and they have x dB power value, then this combination gives you x plus 3 dB power. So, based on that we have calculated a formula that number of devices should be 2 to the power n, where n is given as output power required minus power output from single device divided by 3. So, we will use this formula here. We need 50 dBm here, and our single device can provide us 36.5 only. So, n is coming out to be 4.5. Now, n cannot be a fraction, so we will take it to be equal to 5. So, the total number of devices will be 2 to the power 5 or 32. So, for the second stage, basically we have to put all these power amplifiers, 32 power amplifiers in parallel, and then we will get our P out, which is more than 50 dBm. Now, if you see here, we have done one approximation from 4.5 to we have taken it to be equal to 5. So, because of that our output power will be something different. So, for the last stage, which is a combination of many parallel devices, what will be the P out which it can take? The formula we can take again take from here, P out from the single device, we bring it here, plus 3 times n, and n is coming out to be 5. So, it will be actual P out, which we can get from this is, so 3 into 5 plus the input power, which is 36.5. So, our requirement was that our device should be able to sustain 50 dBm, and with our calculation we have arranged an assembly which is able to give us 51.5 dBm output power. So, it is allowing us more than 50 in fact. So, it is the last stage. So, we have used 32 devices here. Now, if you look at the gain of this particular device, the gain of this particular device here is 48 dB. So, gain is 48 dB, and based on that how much power do we require here at the input of this one? That will be actually 50 dBm which was required minus 48. So, 2 dBm. So, please note that it was the required, and with respect to required we are doing all the calculation. What we actually got, we are not calculating with respect to that, because it is a margin which we are leaving here. So, 2 dBm we want here. If we calculate with respect to 51.5, we will get I think 3.5 dBm, but it is possible that in some of the scenario it will load some of this power amplifier. So, we will keep our calculation with respect to 50, with that it will keep working on a back off. Now, last stage is decided. Now, we are talking about the previous stage to that one. Similar to last lecture, if 45 dBc was our requirement for the last stage, its previous stage should have much relaxed requirement as compared to 45 dBc. So, this stage C by I3 ratio we always assume to be very high. So, let us say it is 60 dBc, And why we are taking this much high linearity requirement? Because the assembly which we are going to connect before this should be linear, otherwise it will load that assembly also. This we have discussed in the last lecture too. So, we have selected this much. So, according to that, what should be the OPBO? Again, let us do the same calculation, and OPBO should be equal to 20 dB here. Now, whichever power amplifier we choose and whatever power that amplifier can give, we have to work 20 dB back off from that. So, let us select our next power amplifier, and that amplifier should be able to give us 2 dBm or more than 2 dBm, so that whenever we apply, our power amplifier does not burn, it is able to provide this power. So, if we look here, now this requirement is quite low. If we choose HPA 272 which has 49 dBm P out at 1 dB compression, we can use this one also. We can use this one also, because if I put minus 20 here, it will give us give me 14. I can even choose this one, it will give me 4 dBm. So, any of those can work now. So, let us choose the first one. If I choose the first one, then again using the same device, it was HPA 272 2 plus, and we were using 32 devices here, and now I use single same device here. The gain is again 48 dB, and it is providing 49 minus 20, so 29 dBm here, although we require 2 dBm, so we are well beyond our boundaries. So, it is good to have this here. So, it is 2-stage amplifier basically with only this single device. So, for this one, what will be our total gain? Total gain will be summation of these two gains. It will be 48 into 2 total gain. (96 dB). Our C by I ratio is maintained easily because we have done the calculation at the output for that. So, C by I ratio is actually 45 dBc, and C by I ratio for this stage will be 60 dBc, and OPBO for this stage was 12.5, and for this stage it is 20 dB. So, this is how we designed by using this stage. Now, we can do we can use another device also. For example, I choose TVA 4W 422A plus. In that case, 34 minus 20, which is 14. Now, solution 1, the second solution can be same assembly here for the last stage, which is calculated for both the solution HPA 272 plus. Okay, so we are talking about solution 2 here, and we are getting, we want 50 dBm and we are getting 51.5 dBm, which is better than this, so it is good. So, it is required one and it is achieved. Now, here we require 2 dBm because of its gain, which was 48 dB. Now, the selected device here, we can use single of that device also, which is TV 4W 422A plus. Now, this one has a gain of 25 dB and we need 2 dBm, but we are getting 14 dBm, which is above this. So, it can stand this much easily. So, it is good to have it here. Now, in this case, if we do the summation of these two stages 48 plus 25, we are getting 73 dB gain, but we require at least 80 dB gain. So, this alone is not sufficient. we have to put one more stage before this, so that we can at least qualify our gain criteria there. So let us put the same device here, or we can put another one. It has 25 dB gain, so if I do the subtraction between these two, it will be minus 9 dBm according to this one, and from here it will be minus 23 dBm. This one will again have gain of 25 dB. So total gain will become 25 plus 25 plus 48. So 98 dB will be total gain in this solution. So as you see, by selecting different devices you will have different solution. So first requirement is to qualify your criteria of P out, of linearity and gain, and once it is done, then you can select your device based on the cost of each of these devices. So the cost is not reflected here, but in actual life when you are dealing with, you are making your setup, you can select these devices based on your cost value also. So this was the example when you can use different devices, and this is where we are showing some calculation for this kind of solution. So one is when we are using the both HP of 272 plus in the both stages, and the second one when we can use any of the other two solution, either this device or this device. Both of them has 25 dB gain, but they have different P1 dB powers here. So based on this we could have done this. Now these are not the only solution, you can mix and match and get other solution. Only for the output stage, you see we always have to select highest P1 dB point, otherwise number of devices will increase, like we have discussed in the last lecture. Now once we have seen the assembly of all this, so based on this let us reflect on two cases. What will happen and how many devices will we require if we do not have to maintain output power back off, and if we can use PA at P1 dB power without compression. What does it mean actually? These are the requirements we want. So 50 dBm we required, and initially because we had to take the output power back off of 12.5 dB, our HPA 272 plus, which was able to give us the P out of 49 dBm, we were only using 49 minus 12.5 dB for the calculation, because we had to maintain the C by I3 ratio. But now we are told that we do not have to maintain output power back off. So what does it mean? It means when we are calculating number of parallel devices, in output assembly, N can be calculated as 50 minus output of the device itself, which is 49 dBm, divided by 3. It will be 1 by 3, and it will be approximated to 1 to make it an integer. Now number of devices required will be 2 to the power 1, which is only 2. Now if you look at this and we compare this with our previous case, we were requiring 32 of such devices when we required that output power back off of 12.5 dB. Now when we do not require any output power back off, we can use all the P1 dB range. We actually require only 2 of these power amplifiers in parallel. So with only 2 power amplifiers in parallel, which are giving us 49 dBm, we are actually getting 52 dBm output power just by using 2 amplifiers. Now it is what we are achieving, and what we require is 50 dBm. Now based on that we can do our next calculations. Again we require 2 dBm power here, and our device which can provide 49 dB power, actually only one of that is sufficient here. So, basically from 32 devices to we come to only 2 devices at the output stage. Now, what will happen if we say okay, we want to have some small output power back off to drive our power amplifier at a linear range, but we want that back off to be very small. So, let us take OPBA equal to 2. So, what will happen in that case? OPBO equal to 2 is given in our condition. So, based on that, let us do our calculation based on this output power back off. So, P out from the device is 49 dBm, but available or useful or practical, we can say, P out from the device which we can take is actually 49 minus 2, which is 47 dBm. Okay, so we have 47 dBm instead of 49 dBm because we are driving at output power backup of 2 dB, and it is given condition in the question here. So, what will be number of parallel devices in that case? Instead of 49, now available power is 47, and if we do the calculation according to this, we are getting exactly 1, and number of devices will be then 2 to the power 1, which is equal to 2. So, we will be using both of the devices here, like in the previous case where we were having no output power back off, but now we can have some small back off of 2 dB, and still we reach 2 devices, and we will get exactly 50 dBm at the output. So, with the same structure and same calculations, we are able to get the better linearity condition with 2 dB output power back off. So, what is the usefulness of such technique? We have seen if we are able to have the output power at P1 dB without compression, then we can reduce our number of devices from 32 to 2 only, and within this 2 also, if we do our calculation properly, we can drive our power amplifier at a little bit back off of 2 dB, and we can maintain all the conditions. So, what is the motivation here? The motivation is there that if there are some linearization techniques we can apply, then we can reduce the number of supplies significantly, and because of that, because each of these devices they consume some power here, they have some voltage value and they have some current value, all of them are taking some DC power. So, number of devices when they go down, then this power consumption goes down, and eventually it is an efficient way of transmitting your signal without any distortion. So, in the next lecture we are going to discuss the linearization techniques, so that we can actually do the transmission without distortion but in a efficient way. Thank you.